All right, let's talk about fluid pressure. Fluid pressure is caused by fluid. And as we sink lower, the fluid pressure increases. Hence, when you get to the bottom of the swimming pool, yeah, your ears are ringing. Okay, fluid has some vocabulary involved. We're going to do rho, which is density, and gamma, which is the specific weight. And the specific weight is rho times g, where g is gravity. All right, on Earth, yes, a capital E, isn't it? On Earth, gamma is equal to 62.4 pounds per foot cubed. It is also equal to 9.81 kilonewtons per meters cubed. Now this is going to change based on elevation and location. These are good general numbers and they're going to be perfectly fine for statics. All right. And we also talked about how fluid increases with depth. So if I have here some sort of dam, and I'll make it concrete so it's all speckly. All right, and we have water that this dam is holding back. This little triangle means that the water is not moving anywhere, because now that's just a totally different problem, okay? As we increase in depth, we increase in pressure. There is a linear relationship. So you'll see here that fluid is a distributed load that is triangular, okay? So depth, we generally represent with y or z, okay? And then we have our height of the water, depth of the water, h, and this is going to give us, just like a distributed load, a resultant force, which if we're representing a distributed load with a resultant force, we need a y bar depth to the center of that resultant force. Now, generally with fluids, we do everything from the surface, okay? Measure all things from the surface. Oh, and the width, okay, if we're increasing with depth, this is going to be gamma h, right? And fluid acts perpendicular to the surface. Remember that air is a fluid. So how do we blow up a balloon? Okay, we blow into the balloon and it expands in the circular shape that is the balloon because there's pressure evenly on all sides of the balloon, making it a circle. Bubbles are a sphere because it's even pressure all the way around, okay? Fluid always acts perpendicular to the surface. So if we look at our first example, okay, getting some numbers on here, given. Gonna put my little dam on here. Put some ground on there. We have some fluid that the dam is holding back. And the entire depth of the fluid here is 12 feet. And I wish to find the resultant force of the water on the dam. Solution. Okay, so we have 0 at the top because I don't have any depth, and then it's going to increase linearly till we get to the bottom. So the maximum value of my distributed load is pressure equals gamma h, which is equal to 62.4 pounds per feet cubed times 12 feet, which is equal to 748.8 pounds per foot squared, because we only get rid of one of those feet, multiplying pounds per foot cubed by feet. Okay, so that means force resultant. My force resultant is equal to 1/2 base 748.8 pounds per foot squared times height 12 feet, and that's going to equal to 4,493 pounds per linear foot into the page. So as we move and the dam is longer into the page, that resultant force is going to increase. So this is kind of like a resultant distributed load. All right, the resultant force acts in the center of that shape. It is a triangle, so Y bar is going to be 2/3 of 12 feet, which is equal to 8 feet down.